We are confused to have seen.
Okay, last time I stopped at this particular problem. I'm going to complete this problem. So it's going to be sort of a review for you if you've already gone through my previous problem on moving a joint from one position to another, but there's an intermediate position defined. So let's read the question and then solve it. Find a time-based parameterization for a revolute joint of a manipulator. The joint should move from 0 to 0.5 radians from t0 to t equals 1, followed by movement from 0.5 rad to 1 rad from t equals 0 to t equals 3. Also, the velocity of the joint at the start of the motion and end of the motion should be 0. And he also told something about the acceleration of the joints at the intermediate part should be continuous. So what I'm going to do is I'm going to write that down in terms of equations first. And once we write those conditions down, then we'll think of a polynomial and then try to find the polynomial. Okay, so here are the conditions. So we're looking at two time-based profiles because there are two distinct motions. So let's call that Q1 and Q2. So Q1, so it should move from 0 to 0.5. So at time t equals 0, the position is 0. At 0.5 seconds, the position is also, well, it is point, my bad. At time equals 1, the position is 0.5, right? At 1, it's 0.5. Okay, then it moves from 0.5 radians to 1 radian. So we're going to assume another polynomial. Let's call that, let's say it's represented by Q2. So at 0.5, it should still be, at 1, it should still be at 0.5. And then at time t equals 3, it should be at 1 radians. So those are the conditions on the positions of the joint. The velocity of the joint at the start and end of motion should be 0. So the velocity, which is q1 dot at the start, should be 0. The velocity at the end, so that's represented by q2, at 3 should be equal to 0. And then you're told that the acceleration of the joint at the intermediate point, that is at time t equals 1, should be continuous, which means that for something to be continuous, the two time profiles should line up. So q1 double dot, that's the acceleration at time t equals 1, should be the same as what you get if you find q2 double dot at 1. Okay. So if you want to have the acceleration to be continuous, you also want to ensure that the velocity is also continuous, right? It doesn't make any sense to have the acceleration to be continuous and the velocity is discontinuous. So we also introduce this condition, which is saying that the velocity is continuous. So what we have essentially there is 1, 2, 3, 4 conditions here, 4 conditions down there, and we have two profiles, Q1 and Q2. So we have 8 conditions, we have two trajectories, two polynomials, Q1 and Q2, and a more democratic way of doing that is to assume that both of them would have same number of constants, which would be the minimum would be 4, right? So 4 for Q1, 4 for Q2. If you have 4 for Q1, then you're looking at a quadratic, third order, right? Third order should have 4, and then Q2 should also have 4. So what we'll do is we'll assume, so 8 conditions. So we'll assume Q1 as a function of time is A11. Let's put it A10. plus a11t plus a12t square plus a13t cube. q2 of t is a20 plus a21t plus a22t square plus. Now because we would need the velocity some point of time and acceleration, what I'll do is I'll take the first derivative of these expressions and the second derivative, and then I'll use it to sub in the condition there, which is for the acceleration. So q1 dot is a11 plus 2a12t 3a13t square. q2 dot is a21 plus a twice a22t plus 3a23t square, and then q1 double dot 2a12 plus 6a13t q2 double dot is equal to 2a22t plus 6a23t. Okay, now what remains is to sub in the values for q1, q2 based on those 8 conditions, generate 8 equations. So sub 8 conditions on q1 and q2 to get 8 equations. Okay, so I'll write those equations down quickly, and you should check me on this. I'm just going to copy, instead of trying to do it slowly, I'll just copy things down, and then you should check if my writing is correct, if the values are right. So q1 0 equals a10, q11 equals 0.4. These are the 8, I'm putting down the 8 conditions here. So one of the conditions, for example, was q1 0 equals 0, and so I just put that value t equals 0 in q1 to get in terms of a's. Okay, those are 4 conditions. We have to still get 4 more conditions. So those are so if you take this condition q one dot 0 equals 0, the initial velocity is 0, you get that equals a11. If you put q2 dot at 3, the end velocity is 0, you get a21 plus 6a22 plus 27a23. We still have 2 conditions more. One is for the velocity, q1 dot 1 equals q2 dot 1, that is ensuring that the velocity is continuous. If you put that, you get 2a12 plus a12 plus 3a13 minus a22 minus 3a23 equals 0. So this, well, I should write it like this. The way I got this condition was q1 dot minus q2 dot, right? So q1 dot is equal to q2 dot at 1, which means that the difference is 0. And so when you take the difference, you get that equals 0. And then similarly, we have q1 double dot at 1 minus q2 double dot at 1 equals, I think I did an error. This is, my bad. This should be, this is the second derivative. Okay, I wrote down the second derivative by mistake. So I'll write down the first derivative first. So that would be a11 plus 2a12 plus 3a13 minus a21 minus a22 minus. Okay, so 8 conditions. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, now clearly this is really hard to solve if you want to solve by hand, because there are 8 equations. In linear algebra, we typically used to solving 2 equations, 2 unknowns, 3 equations, 3 unknowns. That's about it. So do something like this. What you want to do is you want to write it in the matrix form so that MATLAB can then take it and crunch the numbers for you. So what you do is you essentially try to put 1 through 8 in matrix form. Okay, the matrix would look like this. So I need 8 rows for the matrix. And 8 columns, because I need to have 8 unknowns. 1, 2, 3, 4. And then what sits here is A10, A11, A12, A13, A20, A21, A22, A23. Those are my unknowns. And then on the right hand side are the, what goes on the right side are just the right hand sides of those equations. Okay, so right hand side, really I did not write it quite on the right hand side, but 0, 0.5, 0.5, and so on. So 0, 0.5, that is this. Keep going. And then for the rows, you have to do a little bit of eyeballing here. So for example, the first equation is A10. So there's only the only constant there is A10. So what I do is I write 1 here, because when I take this 1, I multiply with A10, I get A1, and then rest is 0, so I need to put zeros such that when you expand this row out, you get A10 equals 0. Okay, and keep doing that. Zero, 0. Okay, so this is sort of the work you got to do, but once you get it in this form, I would call this matrix A, the 8 by 8 matrix. Would call the matrix, this matrix of unknowns as X, and this one as B. So this is 8 times 1 and this is 8 times 1. So if you want to solve for X, it's basically inverse A times B. Okay. There's another command, I think it's A slash A. You have to check this. Not sure if it's A forward backslash, it's forward slash. I think it's forward slash. We can try it out quickly and see. So if you do it in MATLAB, actually, this is actually a more efficient way of doing it than this one. This one takes more steps than this one. They always recommend putting A slash B. I got to check if it's forward or backward slash.
Backwards.
It's backwards. Okay. So when you say A backward slash, that is equivalent to inverse A. This is inverse A. But the way MATLAB does is it doesn't really do, if you know there's something called Cramer's rule, it doesn't do it that way. It has a different way of figuring out the inverse. Anyway, so once you put this in MATLAB, you solve for X. What is X? X's are the A's. You get values for A's. Clearly A10 is 0. A11 is 0. A12 is 0.875. A13 is minus 0.375. A20 is minus 0.4063. A21 is 1.2188. Minus 0.3438. A23 0.0312. So I'll show you MATLAB code where you can plot the response for plots Q versus T, Q dot versus T, Q double dot versus T. See MATLAB. So I'm going to show you MATLAB code which will do the plots for this instead of trying to hand draw them. It's best to use MATLAB. Okay. These numbers you have written down, write those down. I would just take MATLAB output and just copy writing. Again, you don't have to put 1, 1, 1, 1 4 times, but you just put 1, 4. It's really up to you. You don't have to use this. But this is A matrix. That's the B matrix. X equals A inverse P. We can check this A backslash P. So when we print this, X should be the same. So I tried that. Let me. As I said, you can create sections, so you can run parts of the code. Here, let me create a section right here. So I can only run this part of the code and see the output. So you can see the yellow highlight. If you use 2 percentage signs between 2 parts of the code, it will actually take that to be a section. And to run this, you need to go here and say run section. So it will only run the highlighted section. Okay, so it printed something. So this is. So it will print X twice, right? Once using inverse A times B. So that's what you get if you write inverse A times B. This one produced this output. And then let's see what you get if you put A backslash B. The same output, right? So that agrees. So we're good. So you can use either of them. there's no real advantage of using it for small sized a's, but if it's really big A, then you want to use a / b. Okay, so then what I do is I put those in a's, which I define. I need to create the trajectory, so I define length space. So remember, the first half is from 0 to 1, second half is 1 to 3, so there's two length spaces. Then I find q1, find q2, q1 dot, which is essentially take the derivative expression I had there and I put it down there. Okay, and then same for double dot. And so when I run this code, the entire code, I should get three plots, one for q1, q2, that'll be figure 1, then velocity second plot, and so on. So here is, so this is q dot, this is q1. You can see q1 starts from 0, goes all the way to 3. What I've done is I've shown a blue line for the first segment, q1, a red dashed line for the second segment, so 1 to 3. You can see that it is continuous, there is no break. Let's look at the velocity. The velocity, we had asked for 0 velocities at the start and end. That's true. We had asked the velocity to be continuous, so there's no break. Okay, and then look at the acceleration. So if the acceleration, we only specified one condition, the acceleration, that is the acceleration at t equals 1 should be continuous. There shouldn't be any break. But you can see that it is actually discontinuous in the derivative. That is, at this point, the derivative of q dot is discontinuous. So you could introduce more conditions like the jerk, which is at this point should be equal to 0, and then you'll see that it will actually become smooth. Okay, but that's really more conditions would mean that you'll have to replace it with the higher order equations and go from there. So really depends on what you want from the trajectory. Is that clear? So this is one of the problems in the homework. I think there are two problems related to this. Do this and plot. Okay, what I did was finding trajectories for the joint. So if you specify how you want the joints to move, you can create these profiles which are not jerky, very smooth, based on these conditions. You could take the same idea on inverse kinematics. So instead of specifying joint angles, you could specify the position of the end effector. So you could specify x should be 1 through, should go from position, let's say 0 to 1 in specific time, and the velocity, that is x dot, x double dot, have certain conditions, and same for y. And you can create these profiles for x and y instead of q. Okay, so once you specify position for x and y, then what you do is for every point you then do inverse kinematics, so you can get the joint angles. And so this really generalizes to Cartesian space. To Cartesian space is when you want the end effector to move. Joint space is when you want to get the joints to move. You specify everything in terms of joints. Now, before we finish off with this part, I just want to say a few comments about inverse kinematics. Okay, and this is related to your homework, which I think is posted, but I think it's not due next week. It's about reach of your manipulation. These ideas can be extended to end effector trajectory generation the following way. So you define conditions on x of t, y of t. So example would be x of 0 is 0, x of 1 is 0.5, x dot 0 equals x dot 1 equals 0, y dot 0 equals y dot 1 equals 0, and so on. And then you'll find x of t, y of t, because now once you define those conditions, you can find a polynomial and find x and y, and then finally use inverse . kinematics to solve for theta as a function of t or the position as a function of time, right? Because in inverse kinematics, you specify the end effector, which is your trajectory, but you got to eventually control the joints. You can only control theta, you cannot control that directly. So you have to do the inverse kinematics that's shown you drawing circles and so on. So you need to map it to the theta and d using inverse kinematics. For that you need the DH table. If you remember, we used fsolve to do that. Okay, now a few comments about inverse kinematics. Okay, which is given x, y, solve for d theta. So first thing is you want to do is if you are given a problem where you are told to, let's say, get the manipulator to draw something, okay, move somewhere in the space. You want to ensure that the position x, y is reachable by the manipulator. Okay, so if I say draw a figure 8 over there, and my hand can only reach about there, I just cannot draw the figure 8 on the table because my hand cannot reach. Okay, so you have to move the manipulator there. So for that, what you have to do is, before you even solve an inverse kinematics problem, because as I said, inverse kinematics may not exist. You may have multiple solutions, but you also may have a case where the inverse kinematic solution may not exist. And one place people mess up is they just try to make the robot draw at a point where the manipulator just cannot reach. So what you want to do is, once you have a manipulator, you want to find the workspace of the manipulator. What are the places where the manipulator can reach? So my hand can reach only this much, right? And so I can draw anything here, but I cannot draw anything beyond that. So find the reachable space of the manipulator. So if I give you a one link manipulator, okay, just one link, you can only do a limited thing, you can only draw a circle, right? Because you can only sweep a circle, you cannot draw anything inside circle. If you give you two links, then you can do more. So you can probably, draw, if you can stretch the links to any angle, then you can draw everything in the workspace. Line is the workspace. Okay, so there are no limits on the manipulator, and the workspace is the entire red thing. However, if there are joint limits, then clearly you are constrained. Like, for example, I have a joint limit on my elbow joint. I cannot hyperextend my joint, right? A manipulator may be able to do that, but I cannot hyperextend. So that limits how much I can move. And so I think one of your homework problem is, you're good to do the inverse kinematics, but before that, I tell you to plot the workspace when you're given joint limits. So one way to do it is figure out all the joint angles this manipulator can reach, so all the range of motions, and then you just do search. So you just basically put in all combinations for angles and map out the space. Just put dots, and then you'll find the workspace. Once you know the workspace, then you can do inverse kinematics. So that's one very important thing. People don't find solutions because they're just trying the manipulator to go at a place where it cannot go. Okay, the second point is Sometimes the end points are reachable, but intermediate points are not reachable. Okay, when does that happen? So here is an example where you have a manipulator like this. So it's a two-link manipulator, planar manipulator. The workspace is basically going to be an annulus like this. So if you start here and tell it to go there, and you want it to go in this path, clearly that path, you can reach the start, you can reach the goal, but you cannot take the path you specified. This path cannot be executed. So that's why it's very important to know the workspace limits. If you don't know the workspace limits, then you cannot get the manipulator to do what useful things. So that's one of the thing to be aware of when you're doing inverse kinematics. The third thing is there's something called singular configurations. Singular configurations should be avoided. Okay, this is something which I have not yet discussed, but it will come in later on when I talk about Jacobians. Essentially, the configurations are when, let me just draw this. Okay, so it's a two-link manipulator. Starts over here, B. Oh, sorry, it starts, that's the end point. A, this is the start, this is the goal, and the path is this way. Okay, and when the manipulator reaches this position, it's singular. So basically goes that way. It's passing this way, but when it is here, singular. So in singular configurations, typically there are configurations where you would have links to be straight, or they'll be like this. What happens when you reach singular configurations, it's not obvious here because we have not talked about Jacobians, is that certain directions cannot be reached. So for example, if you're here, then you cannot reach any direction which is 90 degrees, which is along this axis, because you lose a degree of freedom. You can only, at this point, you can only sweep an arc. You cannot move that direction, as opposed to being like this, where there's a slight bend, so you can actually reach any direction now because your elbow is bent. But once you are in that configuration, you cannot reach certain points. And what that does is it leads to infinite velocities. And this is something which is you do not have to know right now. Be talking about Jacobians. This is the next part. That's where I will come again, and I'll show you why you do not want singular configuration. So we'll talk about this in the part on Jacobians. Revisit about Jacobians. Okay, so for now, can forget about this. Okay, the last issue is the start and end positions are reachable by different solutions, different configurations. Start and end points are reached by different solutions. What I mean by that will be obvious in a bit. So two-link manipulator, you want it to move from A to B, start, goal. So when you want to reach A, you do this. When you want to reach B, you do that. So why does that happen? You could also reach this way, right? But in this case, this solution is not possible because of joint limit. So not possible because of joint limit. So you cannot get access to this configuration to reach B. So if you were to do this, right, reach from here to here, you could do this, or really flip like this, which is that solution. But maybe I cannot do this configuration, so I have to reach it this way, and then I have to turn my shoulder down and reach point B. One example where this is true is if I tell you to draw a straight line on your back from over here, right, over to there with one hand, then use inverse kinematics of a differential drive car. Okay, so let's draw the car. Here's the caricature of the car. Okay, since it's a differential drive car, we don't show the front wheels, basically a caster in the front. And the car is right now positioned to move, well, it's in the global frame, so X, 0, Y, 0. This is how the car starts. What we are primarily interested here is we want one particular point on the car to follow the curve we want. Okay, that's where you put the pin. Let's say that the point is right here. Let's call this distance Lx, Ly, and that point is where the end effector is. Okay, so that's how the car starts. What we're interested in is a generic position for the car when it has gone sufficient distance and turned. So I'm going to redraw the car at a new time t. The car is maybe this way. Okay, let's call this point E for the end effector. And the car has turned by an angle theta. And if you remember, we defined the width the width of the car is 2W, but W is half width. Okay, and again to refresh your memory, X0, Y0 is global frame. Okay, this is a frame which is fixed. So for example, the corner of the room, X1, Y1 is the local frame, and this is attached to the car. and so it moves with the car. Okay, when we want to draw something, we want to draw it in the global frame. So we are trying to keep track of E in the global frame, x0, y0. Okay, now a little bit of what we've learned for rotation matrices. Since I'm trying to keep a track of E in global frame, I can write xe, ye using some of the things we've done so far in the course. So I claim that xey is cosine theta minus sine theta, sine theta, cosine theta, lx ly plus x comma y. So what's x and y? X and y is the coordinates of point P. Okay, so what this is saying is, if you want to find the coordinates of E, x, E, y, E, okay, x, E, y, E, given the coordinates of x comma y, then this rotation matrix times Lx, Ly will give you x, E, y. So you can check this, for example, if you put theta equals 0, if you put theta equals 0, you get cosine 0 is 1, 0, 0, 1, so you will get x equals Lx plus x. That is, if the car was at an angle theta equals 0, then clearly the x position of E would be x plus xe. That's what you get. So x equals x plus Lx, because you get 1, 0, so Lx times 1 and y times 0, so Lx plus x, and y you see it will be equal to just y. So this agrees. So this is not new. This is something we've done in rotation, probably in the first class on rotations. Okay, so that's the first thing we need to know. Okay, eventually we are trying to get xe, y to follow a path. So it could be a circle, it could be a different curve, it could be your initials, whatever you want. Now, what you want to remember is the only thing you can control for a car is the speed of the wheels. Okay, for the manipulator it was easy because you could just control the joint angles. You could just control theta, theta 1, theta 2, theta 3. In this case, you cannot control the position x, y directly. You can only control the speed of these wheels. So that adds a layer of complexity, because now you can only control the velocities and not the actual angle. So we need to find how to control the speed of the wheels so that you can get x, c, y to follow the path you want. So I'm going to go back to what we derived earlier in the class on mobile robots. So this is so earlier in a previous class, we wrote equations for a differential drive car. So I'm going to rewrite those equations. If you remember, there was equations for the velocity of point P, x dot, y dot, and also the rotation angles theta. And that was expressed as a function of the speed of the left and right wheel and then last one was r times 2w. Okay, I'm going to just write this in a slightly different notation that will make our life easy. X dot, y dot, theta dot equals v cosine theta, v sine theta omega, where v equals r divided by 2 phi dot r plus phi dot l, and omega is r divided by 2 omega phi dot r minus phi dot l. Okay, so this is my second expression. So what this is saying is I can only control phi r and phi l, phi dot r, phi dot l. That determines v and omega. I can totally control v and omega, which controls x dot y dot. So I can control the position p. So p is that point. I can control the velocity of p, x dot y dot. I can also control theta dot, but I cannot directly control x y. So the question is, how do you control x y when the model is in terms of x dot y dot? So what we'll do is we'll differentiate this expression for x dot. You can get x dot e, y dot e, and that's only because we have access to x dot y dot. We already have an expression for x dot y dot. So differentiate one with respect to time. So we can write x dot y dot e equals, go back. When I differentiate this expression, there are really two lines of equations, right? So Lx Ly is the position of the point E, and this Lx Ly does not change because that position E is fixed. So the only thing which I had to differentiate is cos theta with respect to time, so that will be minus sine theta, theta dot, and same for that. And then x, y can also be differentiated to get x dot y dot. So what you get is something like this: minus sine the theta dot minus cos theta dot cosine theta dot and minus sine theta dot Lx Ly, and then you have x dot y dot. Okay, but theta dot is omega. Theta dot is omega, right? It's right here. So what I'm going to do is I'm going to rearrange this equation slightly. Okay. Do that on the next page. Rearrange to get an expression for x dot y dot. So rearrange what? So I did a few things. I not only rearranged it, I also put theta dot equals omega, x dot equals v cos theta, and y dot v sine theta. This came from the expression I wrote down earlier from this. So okay, so what we get is this: Lx cos theta minus Ly sine theta omega plus v cosine theta v sine theta. Okay, we can simplify this a little bit, and before we actually do the inverse kinematics, I'm almost done with the math here. X dot y dot, I'm going to write this in a slightly different way so that v and omega come out of the expression, sort of club them together. Okay, and we have V omega. Okay, the reason I wrote it this way is because remember that we can only control V and omega, right? V determines the speed, forward speed. Omega determines the rate of change of the angle with respect to the horizontal, and we want to eventually control x dot, y dot. Now, the issue, as I said, is we cannot directly control uh, xc and y. We can only control the rate. But the question we are going to do something very smart with x dot, y dot, such that we can actually convert, so that we are actually following xcy and not x dot, y dot. Okay, because x dot, y dot is the velocity. We don't care about the velocity of point t. We only care about the position. So what we do is there's this thing which is we try to sub in the value for x dot, y dot. This is user defined things. We can define it any way we want. So what we do is we specify x dot e to be a proportional controller on the position. So x dot e equals kp x ref minus x c, and y dot e equals kp y ref minus yc. So what does things mean? Kp proportional controller. Okay, kp is a constant, user defined constant. X ref, y ref is the target motion. So for example, if you want the car to draw a circle, then it will be the points in the circle. And xc, yc is the current position of the point E. Okay, so what is the current position? Well, initially the car is such that xcyc is, I think it's lx plus lx. Let's go back. So for example, the current at t, when the car is this way, the position of the end effector is going to be x. The x position is x plus lx, right? X position. The y position is y plus ly, and so that xc and yc is basically the current position of the car. And as the car moves, that position keeps changing. But since we are keeping track of the car at every instant of time, we pretty much know xc, yc. Okay, so we've defined this. What we need to do now is figure out the speed of the car, how the left and right wheel moves. So the last step is put this in that expression and solve for v and omega, because v and omega is things we can control. V and omega determine the speed of the car. So this is number 3. Put 4 in 3 and solve for v omega. Okay, so the expression looks pretty slightly messy, but you do not have to do this inversion if you don't want in by hand. You can actually use MATLAB to do it. So cosine theta minus Ly Lx sine theta minus 1 divided by Lx sine theta plus Okay, solve for v omega at every time step, and then once you solve for v omega, phi dot r is simply v plus solve for phi dot r phi dot l given v omega at every time step. So what we're doing at every time step is we are first solving for v omega, okay, which are related to the speed of the left and right wheel. And if you do that, essentially the equation, the one equation you want to make the car draw is this equation. So if you have this equation, that's all you need to make the car to draw whatever you want. So you specify x ref, y ref, xc, yc is the current position that keeps changing in time, which you can track. You use that to find v omega. From v omega, you find phi dot r, phi dot l, left and right speed. And once you do that, you can draw whatever you want. I'm going to show you MATLAB code which draws shapes using this exactly this idea. So let me first run this code to see what comes out of it. I'm getting the car to draw a circle. Okay, so let me just dive through the code. R is the radius of the wheels, W is half width, L is the length of the car. What I did here was I specified Lx to be along the, so it's a rectangular car, and I specified the end effector or the pen to be exactly in the middle of the car. So that's why Lx is L and Ly is 0. So if this is the car, then the wheels are here, that point is right here. This point is going to track the circle, and you can change it to whatever you want based on your code. The gain is 100. I told you it's a user chosen value. I want to draw a circle, so I specified the equation for circle in terms of the parameter t. T is time, and essentially it is basically takes that equation, which I will show you should be hidden right here. Okay, that's should have my equation now. Okay. Okay, the equation is, sorry, differential drive. That's what the equation is. This is where the equation is. So what I did in this code is, instead of trying to put all of it together as that one equation, I actually broke it down into a bunch of things, and so that it's easier to understand rather than trying to put that formula down. Let's see. Yes, I tried to explain step by step, get the xy position, then get xy position, get xcy from x, then get the error, then get the xe dot y dot, and then hopefully it's easy enough to follow from that. So instead of putting all of it together, in the last expression what I did was I took that whole derivation and did it in steps, and so it's a little bit there's a little bit of code because I broke it into step. But the final step is when you have the position of when you get the speed v and omega, you put it in the differential equation which we derived in the last class, which I started off, and so it's basically taking the entire thing I wrote down and working it backwards. I also have a different curve. That asteroid curve has this equation. So I want to draw an asteroid. It looks like an asteroid. asteroid, basically like this. That's an asteroid, and that's the equation of an asteroid. It has a raised to 3, cos raised to 3, and a sine raised to 3. Okay, and so let's see how the asteroid comes out. Okay, so this is from, there's a PDF I shared, it has 50 curves. You can take whatever curve you want, put it here, and go from there. The good thing about mobile robots is that there is really no joint limits. Right? The only limit you have is the speed, how fast you can draw, but really the mobile car can go wherever you want and draw. It's not restricted to the workspace. This is just showing the velocity, the error. You can play with the gains if you want and see what happens. The KP, this is a user chosen thing. The KP right in the beginning. You'll see that as you decrease KP, you will get problems. Try 10. You will not get a good. Oh, this looks good. That's fine. Let's try 1. If there is noise, then you'll see issues. Yeah, so it's not quite there. That doesn't even complete the curve. So the problem with putting a big gain, well, if you put a big gain, it runs into errors. It runs into singularity. It said singularity is when one of the matrix becomes 0. So when you invert it, it becomes infinity. So you cannot just increase it randomly. Okay, so I'll stop here. Next time we'll do Jacobians. And your homework, you can now do it because I showed you how to do this. Okay, I'll see you on Thursday. I'll also post the first mini project. I'll have to. We're going to be creating a video game using MATLAB. It should be a lot of fun. I'll post that sometime end of this week.